Hello, this is a presentation video from mNAS, Constrained Neural Architecture Search for Microcontrollers. This work is done by me, Edgar Liberis, Lukáš Dudek, and Nick Lane from the Department of Computer Science and Technology at University of Cambridge and Samsung AI Center Cambridge. Now, the goal of mNAS is to enable automatic discovery of convolutional neural networks that are both good at image classification and are also sufficiently small to be executed on a microcontroller. Now, let's look at potential applications of deep learning models with small footprint. One such application is smart home and IoT devices. Now, such personal IoT devices are typically powered by microcontrollers. This is convenient because microcontrollers are small, cheap, and power efficient. Their systems contained within a single chip, and in fact, tens of billions of units are shipped yearly. Now, the downside, of course, is that they lack sufficient computational resources to run these compute-intensive applications. And thus, most devices offload the computation either to a remote server or a companion smartphone. However, if we were able to run deep learning models on the device itself, it would bring a higher degree of privacy, because users' data would never leave the device, and also a higher degree of availability, which would allow these devices to function when the internet connection is either slow or unavailable. Also, this would result in less data being sent to the server, so the servers would be less overwhelmed, and also there will be power saved on the radio communication. Now, let's look at the microcontroller unit from a computational point of view. For our purposes, an MCU will consist of a central processing unit, a read and write temporary memory called SRAM, and finally a read-only persistent storage called flash memory. For IoT-type devices, we will consider mid-tier microcontrollers. Those could be with an ARM M series processor, and in fact they don't have to have floating point arithmetic capability. They only need to do integer arithmetic. They'll have up to 64 kilobytes of SRAM and up to 64 kilobytes of storage. Now, note that this is orders of magnitude fewer resources than a typical smartphone, which is itself orders of magnitude behind GPU-powered deep learning servers. Now, let's map neural network inference to this setup. Each layer of a neural network will be executed one by one in a predetermined order. The CPU will proceed by loading network weights from the read-only flash storage. It will then load the input to a particular layer from the SRAM, and as the computation is running, or when it's done, it will write the output back to SRAM. Now, this is the execution model adopted by TensorFlow-like micro-runtime and CMSIS NN layer implementations. Now, from here we can see how this execution pipeline allows us to more clearly identify how resource constraints may affect the architecture of a neural network. Now, the flash memory of an MCU stores executable code and all read-only constant data. This is shared by the operating system, a deep learning runtime, and neural network weights themselves. And therefore, this makes model size constrained by the amount of available flash memory. Now also, the runtime stores all intermediate buffers, which is mainly activation matrices of each layer of a neural network. And these are stored in the SRAM memory. And thus, the sizes of activation matrices at their peak during the execution must be smaller than the SRAM size overall. And finally, we're assuming that the processor is only capable of executing integer arithmetic, which requires quantizing both weights and activations to int 8. Not only this enables execution, this also reduces the memory footprint of each parameter. Now, let's look at how mNAS implements these requirements to find good MCU-sized architectures. Ultimately, constrained neural architecture search, or NAS for short, is an optimization problem. We seek to find an architecture selected from a predetermined search space that maximizes some target function with respect to constraints. In our case, this is classification accuracy on a validation set with respect to resource usage constraints. NAS has proven itself to be a successful network design tool, with many works optimizing for accuracy within a certain budget of floating point operations. However, we believe the two following design decisions set mNAS apart from the popular mobile or GPU-level systems. The first is a highly granular search space, which means mNAS can control layer arrangement and their hyperparameters very finely. Now, this is required because of this very small memory allowance on an MCU. For example, if NAS were to choose to use a convolutional layer with 33 channels, this may not fit in memory, but the one with 32 channels may in fact fit in memory. Now, the second design feature is an accurate resource usage computation. In fact, we would expect most performant models to lie just below the resource usage caps, which makes it really important to precisely identify suitable architectures and guide the search this way. Now, let's look into how we implement search constraints. Turns out it's not actually straightforward to compute the peak memory usage of a network when it contains branches. At each branching point, the runtime has a choice of which layer to execute next, which then determines which buffers are present in memory at any given time. Now, the buffers store activations of each layer, and these activations can vary in size depending on the operator, which means peak memory usage is actually highly dependent on the operator execution order. Now, in order to compute the smallest possible peak memory usage, we build upon our previous work, which enumerates all topological orderings of a computational graph using dynamic programming. So the example you see on the slide, if we were to follow a default order of 1 through to 7, we would get a higher peak memory usage than if we were to execute the rightmost branch first. Now we turn our attention to latency constraints. It is generally known that the number of floating point or multiple accumulate operations is not actually a good proxy for a latency of a neural network. This is because sophisticated accelerators or GPUs are able to leverage caching and parallelism to quickly execute certain layers. However, microcontroller units do not have these advanced features, and thus MACs are actually a very good proxy for latency here. Now, at runtime, we'll leverage affine quantization, which is built into the TensorFlow Lite micro runtime. This quantization scheme is actually very robust against quantization-related accuracy loss, and thus, for the model size constraint, we simply count each parameter at 1 byte or 8 bits per element. Now, let's discuss the search process. mNAS treats the validation accuracy and all 3 resource constraints as objectives rather than just constraints, which allows it to push the predictive front of accuracy versus resource usage very effectively. Now, in order to explore various trade-off points on this front, we leverage the random scarcization method, which samples an importance coefficient for each objective at each step of the search. Now, the search itself is done using an evolutionary optimization. In particular, we use an algorithm called aging evolution, which works by replacing the oldest architecture in the population by an offspring of a winner architecture, depending on the current selection round. And last but not least, model compression is often used to obtain small models that would not have been possible otherwise. And mNAS actually leverages model compression, namely structure pruning, as it trains candidate models. This makes NAS and pruning actually take a dual role in the selection of the width of each layer, in which NAS chooses the base architecture and then pruning compresses it in a very informed way during training. We have tested mNAS on quite a few popular benchmarks in the TinyML space, and we found that it outperforms both previous and parallel works by quite a significant margin. In particular, I'd like to note the keyword spotting problem on the speech commands dataset. Originally an audio classification task, we turn it into an image classification problem on audio spectrograms. Now mNAS is able to greatly improve on RAM usage and model size for comparable accuracy versus 2 other known NAS for MCUs works, which are MCU-net and MicroNet. Alternatively, if we're targeting smallest possible memory footprints, mNAS is able to deliver higher accuracy than its competition. We also perform a set of ablation studies to decide which design components of mNAS are actually necessary and beneficial for the search. Here you can see 3 graphs where we ran an mNAS search with mNAS, with either the model size constraint missing, the peak memory usage constraint missing, or both constraints present. Now, on the left-hand side, we can see that when model size constraint is missing, peak memory usage dominates the search, which optimizes for narrower and deeper models, which also then result in a higher model size. Now the graph in the middle shows search done without a memory usage constraint, and in this case we see that model size dominates the search, resulting in moderate peak memory usage. But most interestingly, when both constraints are present, mNAS is able to find a balance between the two, which shows that both constraints are necessary and informative and guide the search in a helpful way. Now, to sum up, we believe that successful results of mNAS are largely driven by a highly granular search space and precise constraint computation. In the future, we would like to leverage more sophisticated methodology and other tricks and shortcuts that are typically employed in NAS systems, which would allow reducing search time and targeting larger tasks such as visual wake words or speaker identification. However, even in current instantiation, mNAS is already able to advance the accuracy versus resource usage predictive front for tiny deep learning applications. Specifically, overall, mNAS improves top 1 classification accuracy by up to 4.8%, or reduces the memory footprint by 4 to 13 times, or reduces the number of multiply accumulate operations by at least 2 times. And I hope you enjoyed this presentation. There are more details on other ablation studies, such as the role of pruning, available in the paper, which I encourage you to check out by either following the link there or scanning the QR code. Thank you.